Hi, welcome everyone to the last webinar of this year's series of the EPSC Goes Live for Schools. Today we have Maxime Maurice, who is a French scientist who studied physics, applied mathematics, and engineering sciences, and has been moving around the world. He's going to tell us a bit about his career and how he got from physics to studying exoplanets. So we're very excited to have you here. Thank you very much for giving this talk, and the floor is yours, Maxime.
All right, thank you for the introduction. Hi, everyone. I'm really happy to be here to tell you a few words about the exoplanets, what they look like, how we go about finding them, and I'll say also a few things about, our solar system, the planets that we know the best. And to begin with, I'll also introduce myself a little bit and say a few words about how one becomes an exoplanet scientist. So here we go. Okay, so I'm French. So I grew up in France and I studied there as well. And that's how I started to get into planetary and exoplanetary science. So I grew up close to Paris, capital of France, which is around here. And for my studies, I moved to the southwest of France, which has a long history of aerospace research. There I studied, and then I really stepped into the scientific life when I did my PhD. And for that, I moved to Berlin in Germany. So the PhD is usually the first step into the scientific life. That's when you really get into when you get specialized into a topic. In my case, that was planetary science. So DLR, which is the institution I joined, is the German Aerospace Center, and it's involved into a lot of space missions on the topic of planetary science and exoplanets. And for instance, it's involved in the upcoming mission Plateau, which is this spacecraft, which will be a spaceborne telescope, which will try to find a lot of new exoplanets in the coming years. It should be launched in 2026. DLR is also involved in other missions to bodies from the solar system. For instance, during my time there, that's when the mission Rosetta was active. And the mission Rosetta consisted in these small robots that you can see here landing on a comet. And that was the first time a man-made machine landed on a comet, and the only time so far. And DLR was part of developing some of the tools on these little robots, which is actually not that small. It was also part of the InSight mission, which landed on Mars a few years ago and which finished about 1 year ago, I think, and which brought a lot of new science on Mars. So DLR was part of building one of the instruments on board this mission. All right, at the end of my time there, I decided to go around, see other labs, how science was made elsewhere. And for that, I crossed the Atlantic and I joined Rice University in Houston, Texas. And there I joined a lab of experimental petrology. So what does it mean? That's another way to study planets by doing experiments. And here is a picture of the laboratory where we were working. And experimental petrology consists essentially in taking rock samples and putting them at very high pressure and temperature using these blue machines that you can see in the background. And that allows us to study the rocks in the conditions that you find deep inside of the planets, the Earth or Mars or other planets. So that's what I was doing there. And after 2 years at Rice University, I finished my contract there and I moved back to Europe. So I moved back to France, actually. and joined another lab called LMD, which is where I am at the moment. So LMD is not only a planetary science lab, it's actually a climate science lab. So I have a lot of colleagues who are studying the climate of the Earth. And for instance, some of them are specialized in the climate of the Antarctic. And so every year I have some colleagues spending a couple of months in the French Antarctic base and putting all kinds of instruments to do all sorts of measurements on the climate there. And that's a picture taken by one of them. But some people, including myself, use the tools to study climate, to study the Earth climate, to study other planets' climate, and in particular exoplanets. And I have colleagues, for instance, which use data from space missions observing exoplanets to study the climate of exoplanets. And in particular, you probably have heard of the JWST telescope, which was launched about a few years ago, I would say 4 to 5 years ago, and has really revolutionized exoplanet science because it is just so much more powerful than all the telescopes that we have been working before, that over the last few years, over the last few 2 or 3 years, there is so much more science that we have been able to do thanks of the JWST telescope. And some of the exoplanets that I'm going to tell you about today, we have learned a lot on them just over the last few years. Okay, so enough about myself. Let's dive into science. And to begin with, in science, we like to be very rigorous and we like to be on the same page when we are using some words because we have to use them in a very precise way. So I'd like to start with defining some of the terms that I'm going to be using here. And so it all starts from there. Basically, in space, most things turn around other things. So, for instance, we have moons turning around planets, and planets being usually larger than moons. For instance, we have the moon turning around the Earth, the moon that we know well and can see every night. But there are other moons in the solar system. For instance, it's been known for a few centuries that Jupiter has at least 4 large moons, and Saturn also has 1 large moon. Actually, they have many more, but the other ones are very tiny compared to the big ones. Okay, so but that's not all. Then planets turn around stars. And stars then are also larger than planets usually. So that's small bodies turning around larger bodies. Then stars, they don't really turn about anything. Actually, they do, but that's not so relevant for our points here. But it's sufficient to know that stars are giant balls of gas and which emit light, as opposed to planets, which are small and do not emit lights. Okay, so if we review, moons turn around planets, which in turn turn around stars, which are giant balls of gas emitting light. On this picture, actually, you can see a lot of different stars. Can you see planets? Well, you can't really because they're just too tiny compared to the stars, and they also don't emit light. And last definition is exoplanets as opposed to planets. Actually, it's just a matter of which star you are turning around. If you are turning around the sun, our sun, then you consider the planet. If you are turning around any other star, then you are considered an exoplanet. All right, so with that settled, I'd like to begin with a few words on our solar system, because our solar system is all we have known actually for millennia until a few decades ago when we started observing exoplanets. But observing exoplanets is a very recent thing. And so most of planetary science comes from studying the solar system. And all we've learned with that we then started using it to study exoplanets. But that's the reason why it's still quite important to have a good understanding of our solar system before doing exoplanet science. Okay, so the solar system, our solar system. So as I'm sure you know, we have 8 planets in our solar system. So 4 rocky ones, Mercury, Venus, Earth, and Mars in increasing order of distance from the Sun. And then 4 gaseous planets, Jupiter, Saturn, Uranus, and finally Neptune. That's what's represented here with the Sun, Mercury, Venus, Earth. You have the Moon here orbiting around the Sun. I'm sorry, turning around the Earth, Mars, and then Jupiter, Saturn, Uranus, Neptune. So there's already some interesting things that we can remark here. For instance, you have rocky planets and gaseous planets. And also gaseous planets tend to be much larger than rocky ones. We have a good understanding of why it's the case for physical grounds. But also, it turns out that the rocky planets are closer to the sun and gas planets are further out. And that's not necessarily straightforward. So we are not sure whether that's, a universal law of nature or whether that's just happened to be the case in the solar system, but could be different elsewhere. And that's only when we started observing exoplanets that we could answer this question, whether you could have gas planet close to the star or not. All right. So when thinking about the solar system, it's good to have some ideas of how large things are compared to each other. And that's just not easy to imagine how large a planet is because it's so large that, you cannot really conceive of it. So what I like to do is to imagine that the Earth was the size of a marble. So you have a marble here, it's about, 1.6 centimeter across. So if we have the Earth being about this size, I don't have a marble at hand. Actually, I should have taken one, but it's about the size, of my thumb. So the first question that I'd like you to think a little bit about is, how large you think the sun would be if the Earth was the size of a marble? I will give you a few seconds to think for yourself. Unfortunately, we cannot directly communicate, or I mean, if the microphone is working, um, you can say it in the microphone, but I guess the easiest way is if you think for around for yourself. Okay, so the answer is that if the Earth was the size of a marble, then the sun would be, there we go, 3.5 meter large. So it would hardly fit in a regular intermediate high ceiling room, while the Earth would be just the size of a marble. So that's how big the sun is compared to the Earth. And the sun being the largest body in the solar system. Now with that, let's move on to think about how far away things are from each other. And to begin with, how far would be Mercury from the sun, still in the case the Earth was the size of a marble? So if this Earth was the size of a marble, Mercury would be a little bit smaller, like a small marble. So how far away do you think it would turn from the 3.5 meter large sun? Okay, so the answer is that it would turn around the sun 70 meters away. So it's almost a football field away from the 3.5 meter large sun, which is quite a lot already for this small marble, which would be about this big. Okay, now let's jump all the way to the end of the solar system and think about how far would be the further out. Okay, just before that, here's a picture that was taken a few years ago of Mercury passing in front of the sun as seen from the Earth, taken with a telescope. So you have the sun here, and can you see the tiny Mercury passing in front of it? Actually, that's just here. That's this point. This one here is just a spot. So that's giving you a hint of, how tiny Mercury is compared to the sun. Okay, as I was saying, let's now jump to the end of the solar system. And how far away do you think Neptune, the furthest out planet, would turn around the sun in the case the Earth was the size of marble? By the way, in this case, Neptune would be about the size of a tennis ball, so about this big. Okay, so the answer is, okay, we have 300 meters. Okay. The answer is actually 5.6 kilometers away. So it would take about 1.5 hours walking from the 3.5 meter sun to our tennis ball size Neptune. So that's how far away the furthest out planet is. And that's how big the solar system is or would be if the Earth was the size of a marble. And actually, if we show the distances for all the planets in between, you see that so you suggested 300 meters away. 300 meters away is actually about the orbit of Mars, and the Earth would be about 200 meters away. Okay, so you can see that these distances are quite significant compared to the size of the planets. But now if we move on to exoplanets, that's even another world. So let's just think about the closest star from the sun. Incidentally, we recently discovered that the closest star from the sun, which is Proxima Centauri, also has an exoplanet turning around it. And I will say a few more words about this exoplanet because it's really interesting later in this presentation. But to begin with, let's try and guess how far away the closest star is from the sun, still in the case the Earth was the size of a marble. Okay, so I'll let you come up with a suggestion because it's quite interesting and you might be surprised. I'm curious to know what you think about it. 30
They,
kilometers, right? So
yeah, they said 30 kilometers.
yeah, okay. So that's actually pretty far from the truth. So if
Wow.
the Earth was the size of marble, the closest star from it would be 50,000 kilometers away. So that's more than one times the way across the actual Earth. So that's how far stars are from each other. Okay, and in spite of that, we still manage to observe stars because they emit light, and we manage somehow to observe some of the exoplanets that are orbiting these stars. But I mean, given this gigantic distance, you can easily imagine that it's no easy task to observe these tiny exoplanets which are not even emitting light. So how do we go about doing that? How do we observe exoplanets? So yeah, once again, usually exoplanets are just too far away, too tiny, and too faint to be directly observed. So we have to come up with smart ways to cope with that. And one first way to do it is to take advantage from the case that if you're lucky enough, every once in a while, the exoplanet turning around the stars will come in front of the star and thereby will hide some of the star's light. And that will cause, even though you cannot really see the exoplanet, you can detect, at least the most modern telescope are able to detect a decrease in the brightness of the star. And that suggests, if you observe this decrease coming back regularly, that suggests that there is an exoplanet orbiting this star. And this method is what we call the transit method. And it's really widely used as a detection and characterization method for exoplanets. And here is a little animation on how it works. So that would be the star that you would be observing, but it would be actually so far away that you would not see it as well. But all what you would see is a bright point. And as at some point a planet is passing in front, you would see the light of this star decreasing. Okay? But actually in this animation, you can see the exoplanet. But you have to imagine that 1 pixel would be about this size, so you would not see what's happening within this square. All you could see is the light averaged over this square. And so you would see this decrease in the brightness of the star. And that's how you can infer that there is an exoplanet turning around the star. Okay, a second observation method that I would like to speak about takes advantage of another fact, which is that when an exoplanet is turning around the star, it's not only the exoplanet turning around the star, actually the movement of the exoplanet is also perturbing the star's position, and the star has its own tiny movement, which is induced by the presence of the exoplanet. And that can be detected because the movement of the star, for some deep physical reasons that I won't have time to elaborate on, the movement of the star towards us and away from us is causing minute changes in color of the star. And this also can be detected by the most modern telescopes. And this detection method has a very scientific name, radial velocity method, but that's not so important. But what's interesting about it is that it can tell us how heavy the exoplanet is. And I will show you another animation here. I will just have to quickly unshare my screen and reshare it. So here we are. So this is the star, and this is the exoplanet turning around the star. And you will see that as the exoplanet is turning around the star is also turning a little bit, and that is due to the presence of the exoplanets. So that's how it goes. The star is turning a little bit, and when we're looking at it and we're looking at its color, so it doesn't show here because it's too tiny to really be seen. But if you have very precise instruments, you can see that as the star is going away from us, it's getting a little bit redder. And when it's coming towards us, it's getting a little bit bluer. And when you have sufficiently powerful telescope, you can detect that. And that's another technique to detect and observe exoplanets. Back to the slides now. So this observation method is actually the method which was used to observe the very first exoplanets about 30 years ago. And this exoplanet is called 51 Pegasi b. So it's a very interesting planet because it looks nothing like what we have in our solar system. So, as I said, it was observed in 1995. By the way, the people who observed that got the Nobel Prize a few years ago for the first observation of an exoplanet. So this exoplanet is about twice the size of Jupiter, so it's larger than Jupiter, but it's actually also lighter, so it's fluffier. But what's interesting also is that it's orbiting its star much closer than even Mercury is in our solar system. So it's so close from its star than, so the closer you are from your star, the faster you turn around it. So this exoplanet turns around its star in only 4 hours and 15 minutes. So if you compare it to, for instance, how fast the Earth is turning around the sun, so one turn around the sun for the Earth is by definition 1 year. So on 51 Pegasi b, 1 year is only 4 hours and 15 minutes. That's extreme. So if you remember, when talking about the solar system, I say that we have this observation that the giant gas planets are further out and the rocky planets are closer in to the sun. So here, first exoplanet we observe being completely different. We have a giant planet, gas giant planet, orbiting super close from its star. So that was the first step we took in the exoplanet world, and already it was completely different from anything we knew. Since then, we have observed a lot of similar exoplanets, so very large gas planets orbiting very close to their star. And we have called them hot Jupiters. Jupiters because they are big, giant gas planets like Jupiter in our solar system, and hot because they are orbiting very close to their star, so they are very hot. Okay, another interesting exoplanet that I'd like to talk about is called 55 Cancri e. So 55 Cancri e is much smaller than 51 Pegasi b. It's actually a rocky planet. It's a little bit larger than the Earth, about twice the size of the Earth. And similarly to 51 Pegasi b, it's turning very close to its host star. But unlike it, it's a rocky planet. One consequence of it turning very close to its star is that it's always showing the same face. Pretty much like the moon is always showing the same face to the Earth as it turns around it. 55 Cancri e, we think, at least, always shows the same face to its host star. So it has one side where it's always day and one side where it's always night. And since it's very close to the star, the side where it's always day is super hot. Actually, it's so hot that we think it's covered with molten rock. It's hot enough to melt rocks and to be covered with a magma ocean on the day side of the planet. So here again, something completely different from anything we have in the solar system. There's no planet in the solar system which has a molten surface. So here's another example of how different exoplanets can be from what we know in the solar system. Okay, so yet another example, as I already mentioned, the closest star from the sun is Proxima Centauri. And we discovered a few years ago that it had an exoplanet orbiting around it. And it turns out to be a very interesting exoplanet. It's a rocky exoplanet, so about the size of the Earth, comparable to the size of the Earth. And it's in what we called the habitable zone of the star. So what's the habitable zone? It's a certain distance from the star which allows the planet to have liquid water on its surface. If you're too far away from the star, you are too cold and the water freezes. If you are too close from the star, then that's just like 55 Cancri E, sorry, and you're too hot and all the water is as water vapor. But there's a sweet spot in between, which we call the habitable zone, where you can have liquid water at the surface. And why is it so important? Well, it's very important because we think of liquid water as being a very important condition for life to exist. So basically, no liquid water means no life, at least life as we know it. Liquid water means, well, maybe life. It's at least worth digging further and studying this planet further. And we know that Proxima Centauri B is in the habitable zone, so maybe it has liquid water. And then an even bigger maybe, then maybe it could have life, but we're not there yet. That's for future science to clarify this matter. Another thing that is worth pointing out about this planet is that similar to 55 Cancri E, it's always showing the same size to its host star. So it's far enough that it's not so hot to melt rock, but still it has this permanent day side and permanent night side. So if you imagine there would be life on there, you have to imagine that this life would be on a planet where you don't have day-night cycles like we have on the Earth, but it would have one permanent day area and one permanent night area. So day and night would be places rather than moments. That's really intriguing, and that's also something that has nothing to do with whatever we know in the solar system. All right, and to finish with, I'd like to introduce you not a single exoplanet, but a whole group of them, a whole exoplanetary system, which is called TRAPPIST-1. That's the name of the star. And this exoplanet system has been very, very important recently and is probably the most studied system at the moment. So it's orbiting a very small star called the TRAPPIST-1 star. You can see it's here. So it's not to scale with the planets. You know, the star is still much larger than the planets, but here it's shown compared to the sun. So here you have TRAPPIST-1, and here you would have the size of the sun. So TRAPPIST-1 is much smaller than the sun. But again, it's much larger than its planet here, and that is not to scale. So there are 7 planets orbit, at least 7, maybe there are more that we haven't found yet, but there are at least 7 planets orbiting this small star. And all these planets are rocky, so they are about the size of the Earth. And at least one of them is in the habitable zone. So this E planet, this E planet here is in the habitable zone of the star. The planet B and C are too close from the star and too hot. And very recent JWST observation, which dates back from last year, suggests that at least on planet B, there is no atmosphere, and on planet C, it's not very clear. And planet H is too far away, and if it has water, it's all frozen. But planet TRAPPIST-1e is in the habitable zone, so there's currently a big focus on this planet as well. But on the system in general, because that's one of the most complete planetary system that we have access to, that we know of. And also it has exoplanets in the habitable zone, so it makes it very, very interesting. And the fact that the host star is much smaller than the sun has as a consequence that the orbits of the planets are much closer to it than the orbits of the solar system. And here on this illustration, you can see that the orbit of the furthest out planet of the TRAPPIST-1 system, if you compare it to the orbit of the planets in the solar system, you see that it falls much, much within the orbit of even the closest planet of the solar system, which is Mercury. And so that shows you how different this exoplanet system is compared to our solar system. And the reason for it, again, is that the star is much smaller. So it's much smaller. It's emitting much less light, and that's the reason why all these planets are not frying, even though they are much closer to their star than Mercury is, and including one of them being in the habitable zone. All right, so with that, I think we have a good view of the diversity of exoplanets. The first exoplanet we observed looks nothing like what we have in our solar system. And actually, the more exoplanets we observe, the more new sort of exoplanets we discover, which look nothing like what we have in the solar system. We find some of them which, are pretty similar, but that's not the majority. So over the last 30 years, since we have started observing exoplanets, it has completely changed our view of planetary science, because we have discovered all these exoplanets which are so different from what we had known for a long time in the solar system. And I'd like to conclude with this observation that exoplanets are very different. Some of them are like what we have in the solar system, but a lot of them are very different. And based on that, we can say that maybe the solar system is actually, maybe it's the solar system which is particular rather than the exoplanets being strange. Okay, so with that, I'm done, and I'd like to leave you a chance to ask questions.
Thank you very much. So for the students, if there's any questions, you can maybe ask the questions to your teacher, and your teacher can ask us through the microphone, or if you have a microphone that you can move around, maybe we can hear them. Otherwise, I have one question for regarding exoplanets that you mentioned. There were some that have permanent day and night.
Mm-hmm.
And to me, it's not really clear, and I don't know if for the students it is. It's not very clear why this happens. Like, I mean, I don't know if it happens in many exoplanets, or it just happens that those two that you showed in detail were having this. But like, I feel in our solar system, every planet rotates at a speed that is not the same as their rotation around the Earth, so around the sun, sorry. So now I'm confused as to why this seems to be more common somewhere else. Is there a reason for it?
Yeah, that's a very good point. And actually, as you said, in the solar system, there is no planet which is always showing the same face to the sun. There is, however, one case which I mentioned, which is the moon, which is always showing the same face to the Earth.
Mm-hmm.
And actually, this kind of thing happens when you are close enough when the planet is close enough to the star. So in the solar system, there's no planet close enough to the sun for that to happen, but the sun is close enough to the Earth for that to happen. And in these exoplanet cases that I've shown you, actually, I'm realizing now that it's the case for all of them. I mean, it's not the case for all exoplanets, but it's the case for all those I've been talking about. Because, for instance, in the TRAPPIST-1 system, because the star is so small, the planets are orbiting very close from the star, as you can see here, and that allows them to be in this state where they show always the same phase. And that's the same for Proxima Centauri b, because it's also orbiting very close to a small star. For 55 Cancri e, the star is not that small, but the planet is still orbiting very close to it. And because the star is not small, that's the reason why it's so hot on 55 Cancri e. And on 55 Pegasi b, it's also probably the case. It's just that it's a gas planet, so the gas itself is turning probably a bit differently. But yeah, this is something very common in exoplanets for for one good reason, is that the exoplanets which are orbiting close to their star are easier to observe. And so that's also the kind of planets which show always the same phase to the star. So from all the exoplanets we know, a lot of them are probably in this configuration, even though for all the exoplanets in the universe, that's probably not always the case.
Perfect. I was actually going to ask if this could be somehow a bias of our observation, that we're only looking at those planets that are close enough to their star that we can detect
exactly
them, and not, maybe there is some that is as far away from the star as Saturn, but we cannot really see them for some reason. I don't know.
Yeah, definitely. That's a strong bias.
I think the school wanted to unmute at some point, which tells me there was at least a question from them. I don't know if you tried and didn't manage, and you want to ask in the chat. I think we should be able to hear you now. Okay, there's a problem with microphone.
Okay.
If you want, you can just write the question in the chat, and I can repeat it out loud. So is there any probability for alien life on other planets that we have examined?
Yeah, well, that's the $1 million question, and that's the question everyone is very curious about. But that's a very good question. There are probability, and in order to assess these probabilities, to have an idea of how probable it is, that's the reason why we are trying to come up with characteristics with specific things that would hint at the probability of life existing on these planets. And for instance, that's one of the goals of this defining this habitable zone, is to constrain this probability. So as I told you, if you're outside of the habitable zone, either you are too close from the star, either you are too close from the star and then all your water evaporates, and that's not good for life. Because again, life as we know it needs liquid water. Or if you're outside of the habitable zone, on the other side, you're too far away from the star, and you are too cold, and all the water is frozen. So there's, at least for life as we know it, we would consider there is very little probability that alien life exists in planets which are outside of the habitable zone. And when they are inside of the habitable zone, that increases significantly the probability that life exists on them. But at the same time, there are a lot of other parameters, a lot of them we don't understand very well or at all, that also affect this probability. So we have some way to assess part of the probability, but there's still a big part of unknown in it. And a lot of this unknown comes from the fact that we don't really understand the biology of how life emerged. So we can tell whether there are physical and chemical conditions favorable to alien life to exist, but whether it does exist also relies on biology that we are striving to understand, but still not fully understanding at the moment.
Perfect, thank you. Then they also said studying exoplanets, as you mentioned, is something very recent and that is picking up momentum. Would you say it can be a good topic for today's students to focus on, meaning it would continue for a while and that there will be improvements in the technologies and techniques available to study them?
Yes, so it's definitely a very young scientific field. The first exoplanet, again, was observed 30 years ago. And we can really see the progress that have been made, in particular concerning the instruments. As I said at the beginning, the launch of the JWST telescope is often considered as a new era in exoplanet science, and it's only been on for a few years. So in the field of space science in general, that's definitely one of the leading field, I would say. Maybe some colleagues who are working in other fields would not like me to say that, but I do think it's one of the most active fields. So if you are interested in science, in any aspects of science, because that's also one interesting thing about planetary and exoplanet science, is that you can do that whether you're doing physics or chemistry or biology. A lot of things fit into this under this umbrella. So I definitely think it's something that will be going on for the decades to come. And actually, people are already thinking ahead and envisioning the future missions after James Webb. And there's a few mission projects. For instance, HWO, I think, is planned by the NASA, which is the Habitable World Observatory, which should be another spaceborne telescope, even more powerful than JWST, and which will be looking at other exoplanets, and whose goal will really be to try and identify Earth-like exoplanets, so the one most likely to host life. And in Europe, there's another project which is simply called LIFE, and which is also a project for a spaceborne observatory to detect habitable exoplanets. So in the coming decades, there is really going to be big development. So that's definitely something which I think is worth pursuing as a career. If you are interested by the topic, I think it's there will be a lot of research and science to be done here.
And do you think one day in the future, one of these exoplanets will be reachable by any of our machines? Because I feel like many of the things if I understand this correctly, many of the things we send to space. The problem is at some point we just lose the signal. Like they're so far away that even if they start getting away from the Earth, then we cannot really receive back what they want to send us as information. And do you think one day this limit will be overcome, or will it always be like there will always be a limit of how far we can send things?
So I guess there are two limits here to what you mentioned. The first one is the one you mentioned, which concerns the communication. And the closest exoplanets from us again is Proxima Centauri B, which is, I don't want to say anything wrong, so I think I have it written somewhere. Is about, okay, well, it's a few light years away from us. I would say about 3 light years. I'm not sure, but I think that's about that. 3 light years away. That means that the light of the star Proxima Centauri here takes 3 years from the moment it's being emitted to the moment we see it. And that's also the speed of the light is also the speed of the communications. So when we send spacecraft, we are communicating with them, telling them, you know, what to do, how to orient their solar panels or things like that. And this communication, they travel at the speed of light. So the communication with the spacecraft, if we were able to send one to even the closest exoplanet, would take 3 years just to get there. So if we send a message to the spacecraft, tell it to measure something and then to send it back to us, it would already take 6 years. So that would be, you know, already quite a big challenge to deal with that. But I think an even larger challenge is simply to get there, because it's not like you could easily travel this to the speed of light. Actually, you cannot. That's like a firm physical interdiction. You can only, well, you can travel significantly slower than light. So it would take, I don't know how many years or decades or even centuries to get there. So, I mean, probably sending humans, it's beyond imagination, or at least is reserved to science fiction. There is yet one project which is kind of a bit of a fantasy project, but nevertheless, which has been discussed by some scientists, which would be to send really tiny probes to these probably to Proxima Centauri B, I guess. And the idea would be to shoot a very powerful laser at these probes, which have to be very light, and that would give them enough momentum to travel to a speed which would be approaching the speed of light, and that would make them reach this very far away place in a time which would still be reasonable. But I mean, that's just, you know, that's just an idea, and I doubt it would really be implemented or implementable.
Thank you. Good. Well, if the school has any other questions, we will give it a couple more minutes so they write down and ask questions as well. There's still a few. I will close the webinar. I see people moving, so maybe there is something coming. And I think I will go ahead and thank you very much, Maurice. Maxime, sorry, I keep calling you Maurice. Maxime, for your time and for your amazing presentation. It was really, really interesting. I wanted to thank all the students that are listening and all the people that attended this webinar. And I wish you all have a very good day. Thank you so much for being here. And of course, do not hesitate to contact us, or we can put you in touch with Maxime through email if any question comes afterwards. As these things sometimes take some time to process when we receive a lot of new information. So sometimes it can happen that students have a question that comes afterwards. So don't hesitate to contact us, to contact Maxime, that we're going to also put you in touch with. And thank you very much, all of you, for your time and for this amazing presentation.
Well, thank you very much for having me, and thank you for
They're
the
all waving.
students to come.
Thank you. Bye, everyone.
Bye-bye.